2024, we have a snowboarder of mass m traveling with velocity v1, entering a circular arc at A here. We can see v1. The radius is 6.7. A, B, and C are in a vertical plane. AC is vertical, BC is horizontal. And the student models the motion of the snowboarder, ignoring friction and air resistance. Draw a diagram to show the forces acting on the snowboarder when he's at the point D. We have this angle alpha at the point D. So at the point D, let's say this is it, we have a reaction between the snowboarder and the arc. We have mg coming straight down. Mg, we have alpha, so we have mg cos alpha here, and down the plane we have mg sine alpha. So there are the forces at play here. What can we say? We could set up an equation, or minus mg cos A equals the force directed towards the center, which was mv squared over or mv squared over 6.7. And we're asked to express the reaction at the point D in terms of m, v1 and alpha. So we have position 1 and position 2. So let's look at position 1. Let's look at kinetic and potential energy. So half mv squared plus mgh at position 1 will be equal to the same at position 2. So what have we got here? We have a half m entered at v1, speed v1 squared, plus m times g times the height of 0 at position 1, the height at position 2. So just let's take that right angle triangle out. We have 6.7 and we have A. So along here we have 6.7 cos A, this side here. So if the whole thing is 6.7 from here, from A up to C, this little bit in here, the height for position 2 is going to be 6.7 minus 6.7 cos A. So we have a half m by v2. So I know the next part uses v2, but I'm going to use v2 here. v2 squared plus m times g times the height, which is 6.7 minus 6.7 cos A. So we need this to substitute into the reaction formula here. mv squared, I'll use it. Actually, I'll use it too. I'll use it too here. mv2 squared. So at this point, we need to just simplify it down. It says leave it in terms of m, so let's leave m in and multiply by 2. So we're going to get m v1 squared. We want v2 on its own, so I'm going to bring across this guy. We're multiplying by 2, so minus 2 mg by 6.7 minus 6.7 cos A. Let's bring this guy across to the left. That will be equal to m v2 to be squared. May as well multiply this out. m v1 squared minus 13.4 mg plus 13.4 mg cos A is equal to m v2 to be squared. And we want the reaction in terms of all of these. So the reaction up here, the reaction is equal to mv2 squared, which we just have gotten here, over 6.7, and then that will be plus mg cos A. So we just have to substitute mv2 squared in here. So the reaction is going to be all of this guy, mv2 squared over 6.7, so mv1 squared minus 13.4 mg plus 13.4 mg cos A all over 6.7 plus mg cos A. Actually, there's another mg cos A in the other fraction, so if that's over 1, I'm going to get the reaction to be mv1 squared minus 13.4 mg, and it's going to be plus this guy 13.4 and then plus 6.7 of the same thing, so that's 19 and 1.1 plus 20.1 mg cos A all over 6.7 is the reaction force in terms of mv1 and alpha. I don't think we can do anything else with that. Then we're asked to express v2, which is why I was reluctant to use v2. We're asked to express v2 in terms of v1, but v2 is the speed when it reaches the point B. So let's just look at the diagram again, the speed up here. So ignore my v2 now from the last one. We'll call this one, it's a new v2. So we have position 1, 2, and now we have position 3. So let's look at what we need to do here. I think we need to do conservation of energy as well. So at position 1, mg by 0 plus a half it entered at v1. That's going to be equal to mg, well, it's gone up 6.7 to get to point B because it's the radius. And the speed we're told is v2, so a half mv2 to be squared. This is my new v2. So multiplying, we can't divide by m here, I think. It doesn't tell us we can't. So multiplying by 2, we're going to get v1 squared minus this guy multiplied by 2, which is 13.4 mg. Sorry, just g, we're dividing by m. That's going to be equal to v2 squared. So v2 is going to be the square root of v1 squared minus 13.4 g. At the point B, the snowboarder leaves the arc and moves vertically upwards. So here he is leaving the arc. He's going in this direction. What's happening? Well, mg is going down in this direction. And there's also a resistance force, mkv, going down in that direction as well. He's accelerating, well, he's going up, but his acceleration is negative because he's slowing down. So acceleration in that direction. So if we were to draw the forces diagram here, it would be the forces, even though he's moving in this direction, there's nothing happening there. So it'll be 0 minus mg minus mkv is equal to ma. So we're going to get minus g minus kv is equal to the acceleration. And actually that's what we're asked to show down here. Show dv dt is equal to this minus, if I factor it out, g plus kv. Show that this is equal to dv dt. Well, if v is equal to u plus at, you know that dv dt, if we differentiate this, we're going to get a. So therefore dv dt is equal to this expression here. In part 6, we're asked to solve the differential equation and find an expression for v in terms of t, k, and v1. Okay, what's happening here? Well, let's simplify. First, we're going to get dv over g plus kv is equal to minus dt. So we integrate these. And we know that it at time 0, when time is equal to 0, the velocity is equal to v2. That's what they're telling us here. So that's how we can find an expression in terms of tk and v1. We have an expression for v2 in terms of v1, so it's actually a bit of work involved here. So integrating this is going to be the natural log of the bottom times 1 over the differentiated part of v, so that's going to be 1 over k by the natural log of g plus kv between v and v2 will be equal to minus t between t and 0. So subbing in v, I get 1 over k times the natural log of g plus kv, and then it's going to be minus the natural log of g plus putting in v2 for v, k v2 equals minus t. If I multiply by k, I'll get minus kt on the right hand side, and I can simplify this subtraction of natural logs as a division, g plus kv over g plus kv2. This is to the base e, so I can try and get v out of here. E to the power of minus kt will be equal to g plus kv over g plus kv2. I think we're on the right track here. If I cross multiply g, I can keep it as g plus kv2 for now. G plus kv2 times e to the power of minus kt will be equal to g plus kv, so minus g equals kv. So if I divide by k, I can get an expression for v, and I want it in terms of tk and v1. I have it in terms of tk, sorry, that's a k, t there, not a k. So I need to change v2. I have v1 in terms of v2. We got v2 was equal to the square root of v1 squared minus 13.4g earlier. So I'm just subbing that in here. I think that's all I can do. So then I have everything in terms of v. So v will be equal to g plus k times v2, which is the square root of v1 minus 13.4g. Not the tidiest maths in the world, and maybe not something that's going to make you fall in love with applied maths. That's over k. I can factor out the 1 over k minus g over k. That's my final attempted solution at this question.